Okay, can you see that?
Yeah.
Yes, we can see that clearly.
Okay. All right. So yes. So the second try, I guess, for this talk. 2 weeks later, I will again attempt to talk a bit about the state of the BDK anomaly. So what's the current experimental status, and how can we interpret those results in the context of new physics models, or new physics in general, also model independently. And I think I showed the first few slides already, so I can go maybe quickly to the first couple of slides. So the basic idea is sketched here. Though we're looking at these rare decays of hadrons that contain a B quark, and the reaction that we're looking at is a decay of a B quark into a strange quark, and then 2 leptons here, a muon-antimuon pair. And in the standard model, that is a loop-induced process. It's a very rare process, suppressed by a loop factor and by small CKM matrix elements. And if one measures such a process, one can compare the results with the standard model predictions. And then if there's agreement between those two things, one can put constraints on possible new physics contributions. But if there's a discrepancy between the standard model prediction and the measurement, then one would say there's an anomaly, and one could attribute that to a new physics effect, and then one could get information on the coupling of new physics and the scale that corresponds to such a new physics effect. And what I also mentioned already last time is that in this context of these rare BDKs, if one just puts numbers and assumes that there's an order 1 difference between the measurement and the standard model prediction, then one gets generically a new physics scale of around 10 TeV. So that's a scale that is not yet directly probed at the LHC, or sort of at the border of what can be probed at the LHC. So it is conceivable that if there's an effect that shows up in this rare BDK, whatever new physics it is, it would have not been produced yet at the LHC. So there's this indirect reach to higher scales, and those scales then could be a target for exploration at future colliders, maybe 100 TeV collider or something like that. This slide shows the integrated luminosity that the LHCb detector has been recording over the last decade or so. And in total, the luminosity that they have recorded corresponds to around 10 to the 12 B quarks. So they have a very unique sensitivity to many of these rare BDKs, which have very small branching ratios. But because the LHC produces so many of those B quarks and B-flavored hadrons, one can study these rare BDKs for the first time now at the LHC. And then here is now an overview of the various measurements or observables that show discrepancies between experiment and the standard model predictions, and they are arranged here in a two-dimensional chart. On the x-axis is the nominal significance of this discrepancy, and on the y-axis is what I call relevance of hadronic effects. So the lower down you are, the more you have to worry about hadronic physics, non-perturbative QCD effects that enter in these theory predictions.
Wolfgang, just one request from one of the from Qed. He said that can you speak a little bit slower?
Of course, yes.
A little bit.
Yes, so, I will do that.
Yeah, thank you.
So so the relevance of hadronic effects, that refers to that the entries here that are on the lower side of this chart, that they are affected by non-perturbative QCD effects, and those are hard to control from the theoretical point of view. So you can think of this y-axis as a measure of how reliable the significance is on the x-axis. So you want to be ideally in this upper right corner here, where you have a large significance or a large discrepancy between theory and experiment, but at the same time you also want to trust your theory predictions. So you would like to be here in this upper right corner.
So the reason why the Arcane and Rtstar those are has a less relevance on Harmonic effect because you divide it, right? You divide between the two channels, right? So then
exactly, and I will come to that later in the talk, and we will discuss why those are considered as very clean, theoretically clean observers. As you said, these are ratios of branching ratios, and in these ratios, many of the hadronic effects are cancelling out. So the theory predictions for these observers are very well under control, while things like absolute branching ratios of these semi-leptonic B decays, B to K mu mu, B to K star mu mu, P sub S to phi mu mu, those decays are difficult to predict reliably from the theory point of view, and therefore these discrepancies that are observed there are sort of less reliable. And then there are things which are in between, angular distributions in B to K star mu mu. They have some uncertainties that are hard to estimate, but they're not as bad as these branching ratios. There's P sub S to mu plus mu minus. It's again a branching ratio, but now a purely leptonic branching ratio. So there the hadronic physics is much less complex, and it's also easier to predict that with high precision in the standard model. So this is a sort of more reliable discrepancy, even though the significance of that thing is not very high. It's only around 2 sigma. So overall, there are these various discrepancies. I also added G minus 2 of the muon as a comparison. I think their significance is very high, more than 4 sigma. And in terms of sort of reliability, how well do we trust actually our theory predictions? I think that's G minus 2 sits somewhere in the middle of all those various B anomalies. And in the context of these B anomalies, one distinguishes between these B to S LL flavor changing little current decays, these rare decays, which are circled in red, and then there are also anomalies in charged current decays. When one has a B quark decaying to a charmed quark, a lepton and a neutrino. These are these observers RD and RD star. And again, these are ratios of branching ratios, and I won't talk much about those in this talk. I will focus on this rare B to S LL decay. So we will talk now in the following about this. Well, first of all, about the individual branching ratios that are shown here. Branching ratios of B sub S to mu plus mu minus, branching ratios of B to K mu mu, B to K star mu mu, B sub S to phi mu mu. We will talk about these angular observables in B to K star mu mu, and we will talk about these lepton flavor universality ratios, RK and RK star. And we will discuss what's going on there, and if there could be new physics that is leading to these discrepancies.
Question.
Yep.
You did not include the
Julia, your voice is so small.
Really? Sorry.
Yeah.
I can't hear anything at the moment.
Yes.
He has problem with his mic.
Okay.
Sorry, can you hear me now? Can you hear me now? No, it seems not.
Slightly better. Just
Hello, can you hear me now?
Yes.
Hello? Okay. You did not include, maybe you were aware about this, the zero apparent CP violation in B sub S system found about 10 years ago, when they measured the anomaly to dimuon events, the
Yes.
asymmetry of dimuon event, and it seems there is no such progress after that.
Yes.
After the breakup of the D0, what is the status of that observation?
Yes. Very good. Yes. So this was a measurement that was sort of unique to D0. So I'm not aware of any other experiments that try to measure the same quantity later on.
Mm-hmm.
So what that was, if I remember correctly, this was what they called a like sign dimuon asymmetry.
Mm-hmm.
So they looked for events with 2 positive muons versus events with 2 negative muons, and this symmetry. So the standard explanation of that would be that this comes from CP violation in B meson oscillations. But from what we know now from other measurements of B meson oscillations is that it can't be that, because the amount of CP violation that we observe in B sub S meson oscillations is very small. So whatever they saw at D0 is probably something else, but not CP violation in B meson mixing. I don't think it has been clarified what that was, and I'm not aware of any experiment that could actually repeat that measurement that D0 made.
I remember at Fino meeting, this Amarjit Soni criticized that experiment. He said it's very weak experiment and it should not be done. He said.
Okay. Yeah, don't know what if I can say much more about that. The only thing I know is that it is sort of unresolved to some extent. Okay. I mean, this measurement exists. It shows a discrepancy, but there's no known standard model explanation and also no known new physics explanation of it.
And we cannot verify it because it's unique. Okay, thanks.
Yeah, so for the rest of the talk, I will focus on these rare decays. And the first we will look at is B sub S into me plus, me minus. So that's a bound state of a B quark and a strange quark. So B sub S meson, it decays into a muon antimuon pair. So it's sort of arguably the simplest example of this quark level B to S mu mu transition. And what is being done at the LHC, so both by LHCb, but also actually by CMS and by Atlas, is that they measure the branching ratio of this decay mode, and there's a slight tension, sort of a 2 sigma tension between the standard model prediction and the experimental result. So what is shown here in red is the world average of the measurements from LHCb, CMS, and Atlas. So the central value is around here, and the standard model prediction is up here. That's B sub S to me plus or minus, and also B0 to me plus or minus, so both of these branching ratios. And there's also a 2 sigma-ish tension between measurement and standard model prediction. That by itself wouldn't be super exciting. It's only 2 sigma or slightly less than 2 sigma, but as we will see, it fits nicely into this picture of the other anomalies. And the next thing we will look at are these semi-leptonic decays. So here's an example. Now a B meson. Now here the example of a charged B meson, a bound state of a B quark and an up quark, decaying into a kaon, which has a strange quark in it, and then again a muon anti-muon pair. So now it's a 3-body decay mode. And what one can do here is one measures differential branching ratio. So one measures the branching ratio as a function of the invariant mass of the muon anti-muon pair. And this also has been done at LHCb in particular. They have many results of these differential branching ratios. Here's the example of B plus to K plus, B plus V minus as a function of Q squared, which is the dimuon invariant mass. Here's the example of B0 to K star 0, me plus V minus. Here's the example of B sub S to phi, me plus V minus. And in all those cases, one sees that the measured values, the various crosses, black and gray crosses here in these plots, in all those cases, the measured values are systematically below the standard model predictions, which are these colored boxes and regions in the various plots.
So some stupid questions. It's because I'm not that familiar with this anymore. So what is the Q squared?
Yeah, Q squared is the invariant mass of
why there is no. Okay, sorry. So just 2 questions, just to finish. So what is Q squared, and what is this hole like at some places with Q squared?
Good.
Thank you.
Yes, you can see it in this plot here. So they have sort of blacked it up or graded out. It's shown here shape psi and psi to S. So these are backgrounds. In this region of Q squared, you have large backgrounds from muons that come from the decay of shape psi or from psi to S. So the shape psi and psi to S, these are germanium resonances, and they have a mass which exactly corresponds to a Q squared in around those values.
So Q squared is the invariant mass of the 2 muons.
Exactly.
Nice.
so they simply mask out those regions because they have tons of muons which come from those decays.
Right. Which is not related to this decays, just happens to be
yes,
so
it's not related to that decay. Yeah. So it's a decay of a p meson into a kaon or a k star, and a shape psi or a psi to s, and then afterwards the shape psi or psi to f decay into muons, and so those are simply taken out.
So you can take the data, but still you don't know how reliable the data is, right? For example, in the top plot, I see. Patipan has a question. You can ask Patipan. What is it?
Okay. Sorry. I'm just wondering. So, what is the SMLCSR? What that stand for? The prediction.
Exactly. So LCSR stands for light cone sum rules. So that's a method to predict the form factors that you need to make the standard model predictions. And lattice is for lattice QCD. And then there are various ways to do these calculations. Some people like this lattice calculation. Some people like light cone sum calculation. Some people combine the information and then sort of do a combined thing. And depending on what you do exactly, you get different predictions from the standard model. And one can argue, or one can wonder of how reliable these uncertainties of the standard model prediction are. Maybe these the size of those boxes is maybe somewhat underestimated. Maybe you should increase the size of those things, and depending what you do exactly, you get different answers and of how significant these discrepancies really are.
Okay, thank you.
But they do look consistent, right?
Yes. I mean, from this plot here, the red boxes and the blue boxes, they overlap, so there's consistent. Well, yeah. So from the lattice thing is used here, the icon summaries are used here, and then the combination is used here. Though, yeah. So there's consistency between these different determinations, but still one can argue if how reliable they really are and how well controlled these various predictions are. And people debate a lot about that, and so it's later when I show you the results of fits that we are doing, I will always distinguish between a set of observers which are clean and a set of observers which includes everything. So the set of clean observers wouldn't include those branching ratios, for example.
I have another question.
Yep.
In the left upper plane, why the band the green band cut there? There's a gap.
Yeah, that's essentially the same reason why also the experimental points have these gaps. Also from the theory side, it's very hard to predict what exactly happens in that Q-square region, because you have these germanium resonances, and it's very difficult to describe them theoretically. So one decides just to sort of give up on that region and just concentrate on Q-square regions which are free from this contributions from germanium resonances.
Okay, thank you.
Okay, then here's another example of one of those rare decays, now a bit more complicated. Now we have a B to K star, mu plus, mu minus, and then the K star decays further into a kaon and a pion. That's sort of a two-step process. We have a B meson going into the excited kaon, the K star, mu plus, mu minus, and the K star going into a kaon and a pion. So one has now 4 particles in the final state. And one can define all kinds of kinematic distributions in that case, in particular angular distribution. One can look at angles between the muon and the K pi system. One can look at the angle of the kaon versus the dimuon system. One can look at angle between different decay planes and stuff like that. And here, just for illustration, is one event display of such a decay. So in the middle here is the primary vertex where the protons collide, and a B meson was produced. The B meson travels a certain distance to the secondary vertex, and in the secondary vertex you get a mu plus mu minus pair, and also a kaon and a pion. They all point back to this secondary vertex. So that would be one event display of such a B2K star, mu decay, where the K star decayed into a kaon and a pion. And then one, as I said, one can look, for example, at angles between those various decay products and look at the various angular distributions. And one such observable that characterizes the angular distribution is called P5 prime. It's some angular moment of that distribution. And again, it can be measured as a function of Q squared, the dimuon invariant mass. And that is and what is shown here are results from 5 years ago, so a bit more than 5 years ago, where the orange and the purple is again standard model predictions, and then the various crosses are measurements, and the measurements from LHCb, Atlas, Bell, CMS. So LHCb ones are the most precise, and they show some rather significant discrepancy here, at least in this Q square region. And so this P5 prime observable is off by something like 2.5 sigma in a couple of bins, at least in this early data from 2015. And since then there have been updates. So earlier last year, so beginning of 2020, there was an update of this P5 prime observable, now with part of the run 2 data, and this discrepancy persists, also including the new data. So the central values more or less stayed where they were. The uncertainties went down a bit. So it's again 2.5 to 3 sigma discrepancy in this Q square region here. They also have a measurement of P5 prime in a different system. So what I've shown here, that is a decay of a B0 to a K star 0 mu mu. And here they also look at the decay of a charged B meson into a charged K star and mu plus mu minus. There, this measurement is more difficult. So they have less statistics. So the uncertainty of the measurement is much larger, but they see the same trend in this Q square region. They have measurements which are above the standard model predictions, and that came out a year ago or so. Still, for these angular distributions, there are somewhat sizable theory uncertainties, and it's not exactly clear how robust the theory predictions are. So here one can still argue that maybe one shouldn't be too excited about these discrepancies, because maybe the uncertainties on the standard model predictions are somewhat underestimated, and if one inflates those, then the discrepancies actually are not as severe as they might seem. And then now we move on to the last set of observables. These are these lepton flavor universality tests, or lepton flavor universality ratios, RK and RK star.
Sorry, Wolfgang. What is definition of P5 prime? What quantity is about?
Yes. Let me check if I have a backup slide. I forget if I. Sorry. Yes. So okay. I don't know if that helps, but so what is shown here is the most general expression for the angular for the fully differential angular distribution of that decay. So there's Q squared, and then there are 3 angles. So the 3 angles are shown in this sketch here. There's an angle between the muon and the K pi system. There's the angle of the kaon with respect to the dimuon system, and then there's the angle phi, which is the angle between the 2 decay planes that are spanned by the dimuon system and the K pi system. But just based on the quantum numbers of those particles, one can write down the most generic form that the angular distribution can have. And then there are these coefficients that are called FL, S3, S4, S5, etc. And P5 prime is a particular combination of S5 and FL. So it's I think it's S5 divided by the square root of FL times 1 minus FL. So it's a funny combination of these coefficients in the angular distribution.
And it's sensitive to, it's sensitive to new physics. Right?
It is sensitive to new physics. So it also is to some extent sensitive to the chirality structure of the underlying interaction. So if it's a left-handed current or right-handed current, or it's a vector current or axial vector current, depending on what you do, you affect some of these coefficients and others not. So depending on which combination of those coefficients you take, you can design observables that are particularly sensitive to a particular type of new physics.
Okay, thanks.
Okay. So now to this lepton flavor universality tests. Arcane and Rtstar, they are defined in Z way. These are now ratios of branching ratios of B2K mu mu over B2K EE, or B2K star mu mu over B2K star EE. And the standard model predicts that these ratios should be 1 with very high precision. So even though each individual branching ratio is subject to large hadronic uncertainties, in the ratio, these uncertainties cancel out because QCD is lepton flavor universal. It doesn't depend on the lepton flavor. So both numerator and denominator are affected in the same way by these hadronic effects, and therefore the ratio is 1 with a very, very high precision. And our last year the situation was the following. There were various measurements of such ratios of Rk and Rkstar in different bins of Q squared. So these things in the parentheses up here, they show different Q squared bins, and all those ratios were measured to be below 1. So it's like between 15 and 35% below 1, with uncertainties which are such that these are deviations from the standard model by 2 to 2.5 sigma. There's also a measurement in a baryonic decay, so a lambda B baryon decaying into proton, kaon, and 2 leptons. Also there they have a measurement of this lepton flavor universality ratio, and also there they see something which is below 1, even so with larger uncertainties. And then earlier this year there was an update of the Arcane measurement with the full run 2 data set, and the central value, if you look at the central value stayed exactly the same as before, but the uncertainties went down by around 50% or so. So we have now this measurement of Rk of around 0.85 with uncertainties of around 0.04 or 0.05. So that's a 3 sigma discrepancy with the standard model prediction of 1, though. So LHCb now claims they have evidence for lepton flavor universality violation in these B2K LL decays. And then very, very recently, just less than a couple of weeks ago, there were new measurements of Arcane Rkstar. This time they're using slightly different decays. They're using not a charged B meson decaying into a charged kaon, but a neutral B meson decaying into a K short and L plus L minus, or a charged B meson going into a charged K star, which then decays into a pi plus and a K short and L plus L minus. And those measurements are more difficult because the K short is hard to detect. But they find central values which are below 1, something like 30% below 1, and quite large uncertainties because this is a difficult measurement. But again, something like 1.5 sigma below the standard model prediction, and in agreement with this trend that all of those ratios seem to be below 1. So there seem to be less muons than electrons that are produced in these decays, which is also compatible with assuming that the electron branching ratios are actually standard model-like, while all the muon branching ratios are below the standard model prediction. So that is actually also compatible with the results that I showed at the beginning, where the individual branching ratios into muons seem to be all low compared to standard model predictions.
Sorry, Wolfgang, just to clarify, maybe I misheard you. So there is the one that we show here is the ratio, right? And you mentioned that the electron is equal to with the standard model prediction, and the muon is lower, or it's not the other way around, where the muon stays the same and the electron is slightly higher.
If you only look at these measurements of Rk and Rkstar, etc., then that is a valid interpretation. So the measurement of R itself doesn't tell you where the discrepancy is, if it's in the electrons or in the muons. But what I'm saying is it is compatible with assuming that electrons are standard model-like and muons are suppressed. And that is compatible with the measurements of the individual branching ratios of muons.
Oh, I see. Okay, sounds good. Because you have BS to mu mu and the other. Yeah, I see.
Yeah.
I see. But there is no measurement of BS to EE, for example, right?
No, so there's no separate measurement.
Test that. Yes, you cannot really test that assumption that BS, the EE is standard model like, at least for now.
Right. It is an assumption, but it is an assumption that is compatible with all the information that we have.
Right. Okay. Thank you.
So by the way, why is the electron more difficult to measure, or they just didn't want to bother measure the electron?
Oh, it is difficult because the main reason is that muons are simply much cleaner in the detector. Muons leave a very nice track and they travel very far out. They have dedicated muon chambers to see the muons. So muons are very easy in some sense to detect. But electrons are more difficult. Electrons, they reach the electromagnetic calorimeter and then they leave a sort of a spray of stuff in the electromagnetic calorimeter. But they're more difficult to detect, to measure the energy, and momentum is more difficult. Electrons tend to radiate more photons, so the Bremsstrahlung from electrons is much more frequent than from muons. That means electrons, they lose more energy through Bremsstrahlung, and then you have to try to figure out can I recover that Bremsstrahlung somehow and then add it back to the energy of the electrons and the momentum of the electrons when those things are measured. So electrons in general are just much more difficult from the experimental point of view.
I see. Thank you.
But in theory, they can measure it, right? I mean,
yes. I mean, in some sense, that's what they do when they do this RK and Rtstar measurements. I mean, the nice thing is for this ratio measurements is that for them many of the uncertainties cancel out, and then it's easier from the experimental side to do that ratio measurement, and it's also easier from the theory side to make a prediction for Arcane and Rtstar because all these Adronic uncertainties cancel. So in that sense, it makes sense to do this ratio measurement instead of measuring the branch ratios individually, even though you sort of lose part of the information, of course.
Yes, when in theory, in one day, if they have the data sitting there, right? When they have time, and, whenever it is like when the LSC turn off forever, for example, then they can start to do that measurements, or they can start to do the analysis like that. Okay. I
mean, for now, I mean in some sense, what one could do is just to take the measurement with the muons and multiply it by this or divide by this ratio measurements.
Right.
That sort of would be effectively the thing that one would get, but I don't know how close that would be to the actual measurement if they really do that.
Yeah. Okay. Thank you.
Okay. So I mentioned always that the standard model predictions for Arcane and Rtstar are very robust. So one slide to argue why that is actually the case. And at leading order, that ratio, as you said, should be 1, because in the ratio everything should cancel, and none of those decays I mean, none of those decays, the flavor of the leptons really matters. It's always a Z boson or a photon or a W boson which couples to the electrons and the muons, and those couplings are the same in the standard model. So the ratio should be 1. There will be some phase space effects because the muon is heavier than the electron. You should get an effect of order the muon mass squared over Q squared, but those are tiny effects. So unless you are at very low Q squared, these are tiny. These are per mil level effects, and those phase space effects, they are sort of uncertain. So there are Adronic corrections up to the which cancel the ratio, but they don't cancel precisely. They only cancel up to these phase space effects. But because the phase space effects are tiny, all those corrections they are also tiny because they get multiplied by these ratios of muon mass squared over q squared. What one could worry about are QED corrections. So again, these Bremsstrahlungs, the fact that electrons radiate much more Bremsstrahlung than muons. So there are now QED effects which are suppressed by the fine structure constant, but they could be enhanced by large logarithms of electron mass over muon mass, and people actually did look into those things very, very carefully, and it seems that those QED effects are under control. So in the experiment, what they do is actually simulating these effects. So they are simulating the Bremsstrahlung and taking this into account when they do the measurements. So putting everything together, what we know is that these ratios, these RK ratios in the standard model, they should be one with % level precision in the standard model. If one looks at differential distribution, so if one would look at, for example, at lepton flavor universality ratios of angular distributions, for example, if one looks at a P5 prime for electrons and for muons, then one has to be a bit more careful, I believe. Then there might be large QED effects that do play a role, and I think this is something that has not been studied very precisely so far. Also because there are no measurements of P5 prime in electrons yet, but if they will be done at some point in the future, then I think one has to be careful with the zero interpretation there and make sure that one actually does understand the theoretical uncertainties that play a role in this context. But for this ratio, for these RK star ratios, the zero uncertainties seem to be very, very well under control. Okay, how am I doing this time? I'm afraid that I'm going very slow.
You are doing fine.
Okay.
This we still have about 20 minutes plus. Like these guys, these guys are fine. They
okay.
You like to discuss stuff better than don't worry about the time. As long as you can get safely.
Yes. All right. Okay, so we have all these discrepancies now in branching ratios, both of the B/S plus or minus rates, and for the semi-leptonic decays, we have these anomalies in the angular observable P5 prime, and we have anomalies in this lepton flavor universality ratios. So, so what could be the origin of all of that? Experimental issues, maybe. I mean, being a theorist, I'm not really qualified to comment too much on that. I guess there could always be something that was overlooked in the experiment, but there's nothing which sort of where people would be wondering about if there's something really wrong with the experimental analysis or so. So most of these things seem to be well under control and well established from the experimental side. Statistical fluctuations could be an explanation. I mean, all of those discrepancies are at the level of 2 to 3 sigma. So each individual one could very well be a statistical fluctuation. It's sort of puzzling that all of them, that there are so many who show up in this rare decays, and that all of them seem to be going into the same direction. So that's not something you would expect from statistical fluctuations, but I don't think one can fully rule that out at the moment. Parametric uncertainties. So what I mean with that are things like input parameters that are not very well known. Things like CKM matrix elements, which enter into the branching ratio predictions, for example. And if the CKM matrix uncertainties, for example, are underestimated, then this could lead to significant shifts in the theory predictions of B/S plus or minus, and also of the various other semi-leptonic branching ratios, B2K mu, B2K star mu, B/S to phi mu. So some of these things could maybe be explained by something like that. underestimated hadronic effects. So those are additional things. These are non-perturbative QCD effects that are relevant both for the semictonic rates and also for the angular observance in B2K star, B plus, U minus, or in P5 prime. So those things might be not very reliable. The way they are estimated at the moment, from the theoretical point of view, this lattice QCD calculations, these light cone summary calculations, maybe they are not as reliable as one would think, and then some of these things could be explained by some unknown hadronic effects, unknown non-perturbative QCD effects, or it could be new physics. That of course is the most exciting possibility. One interesting aspect is that these lepton flavor universality ratios, they are insensitive to parametric uncertainties and underestimated hadronic effects. So they are theoretically very clean. So for them, the only option is either statistical fluctuations, something wrong with experiment, or new physics. I don't think there's any other explanation. And statistical fluctuation, I think, starts to be looking less and less likely, because the central values, they all seem to be piling up at around the same value, and uncertainties are getting smaller and smaller when more data is being added. So it doesn't look like a statistical fluctuation. Though maybe in the not too far future, with more data, with more precision, this statistical fluctuation could also be ruled out as an option, and then we will be left with experimental issue and new physics effect. But for the rest of the talk, I will just assume that there is some new physics in those decays, and then one can check which new physics it could be, and what would be the implications for new physics based on those anomalies. And just a very generic comments about how this new physics interpretation typically works. So one starts out with some model-independent new physics analysis. So one parameterizes new physics effect in an effective field theory. So, for example, things like SMEFT, or the standard model EFT, or something LEFT, which is known as a low energy EFT, so something which is valid at the scale of the B meson. So where you have already integrated out the heavy standard model particles like the W boson and the top quark and things like that. And in that context, one needs to make just a minimal set of assumptions. The only assumption that one basically makes is that the new physics is sufficiently heavy that it can be described by such an effective field theory. So it has to be heavier, it has to be somewhat heavier than the B mesons. And then whenever that is the case, this EFT description works. And then in the next step, one could go to simplified models. So one tries then to introduce a set of new particles, sort of in a minimal way. Let's say a single leptoquark or a single C prime boson, and then one needs to understand what are the required couplings and masses of those particles in order to reproduce the effect one has identified in this model-independent framework. And then, as a third step, one could try to embed then the simplified models into some more motivated scenarios, some sort of a larger new physics scenarios which address other open questions in particle physics, like the hierarchy problem, standard model favor puzzle. Maybe they have a dark matter candidate or things like that. And in that, at that level, someone also needs to ensure that the model is realizable, that it's UV complete, that it has all kinds of nice and meaningful quantities, and that this model then is self-consistent at high energies. And but in this talk, I will mainly, on the rest of this talk, will mainly focus on this EFT framework, and then say a bit about simplified models as well. So the EFT framework is sketched here. So one writes down an effective Hamiltonian which contains all possible dimension 6 interactions which can mediate the B2S LL transitions. And there are several of them, and they are very well understood and enumerated. There are these dipole operators, B2S photon operators. They come with Wilson coefficients, C7 and C7 prime, and they correspond to this, so these dipole interactions between B quark, a strange quark, and the photon field strength tensor. And when the photon goes into mu plus mu minus or E plus E minus, you get this B to S mu mu or B to S E decays. The other set of operators are these semi-leptonic operators, or also scalar operators, which are 4 fermion contact interactions where you directly couple a quark current, a B to S current, to a muon current or an electron current. And those various interactions, they come with coefficients called C9, C9 prime, C10, C10 prime, or then the scalar currents with CS and CS prime. And the most important ones in the following will be C9 and C10. So those are left-handed B to S currents, and then either vector currents for the leptons or axial vector currents for the leptons. So C9 is the vector current, C10 is the axial vector current. And what one then often does, well, first of all, there's a lot of information that one needs to take into account. So if one switches on one of these interactions, so if one switches on one of these Wilson coefficients, one typically will modify not only one observable in one decay mode, but one will modify many things simultaneously. These dipole operators, C7 and C7 prime, those things, they will modify in particular these radiative decays of B mesons, B to K star gamma, for example, or the inclusive B to XS gamma, where XS refers to anything that contains a strange quark, or also things like B sub S to phi gamma. Also, these things will be heavily impacted by any physics in these Wilson coefficients C7 and C7 prime. But they also impact these semi-leptonic decays, all those things that we discussed, B to K, mu mu, B to K star, mu mu, B sub S to phi mu mu, also baryonic decays, lambda B to lambda mu mu. If you look at C9, C10, and this scalar operators, again, there will be many different decay modes that are affected simultaneously, and in each of those decay modes, many observables will be affected, not only the branching ratios, but potentially also angular observables or these lepton universality ratios, etc.
So why doesn't the C7 affect the B to S, BS to mu mu, BS to mu mu, right?
Yes.
So you can draw a diagram.
Right. You could draw the diagram, but what happens there is it's essentially you can argue, or one way to argue would be that this vector current is conserved, and what you find is that if you apply equations of motions for the muons that go out, you find that the rate is simply zero.
Okay. Okay.
So and the same happens for C9. So whenever you have a vector current for the leptons, and you couple that to a pseudoscalar or scalar, so the B sub S is a pseudoscalar, and you sort of it's a spin zero thing that is decaying into 2 spin 1/2 fermions through a vector current that simply is zero.
Okay. Yeah. Okay. Thank you.
Yeah, but so there's this. I mean, the main point is that there's this complementarity between all those various decay modes. Each decay mode has sensitivity to a particular combination of Wilson coefficients, or each Wilson coefficient depends or affects a certain range of processes and observers. So what one typically does is to do global fits, and I have been doing these things since quite a long time now, almost, I think, 10 years I've been working on these type of things. And here's just a list of the most recent papers that came. Actually, I think I forgot. I think after the result that came out a couple of weeks ago, I think there were at least 1 or 2 new papers which I forgot to put on this slide. But those were the range, the set of papers that came out after the NHCB update of Arcane earlier this year in March. So if you look at those papers, you typically will find then tables or plots of Wilson coefficients and the best fit ranges for those Wilson coefficients. And I just want to go through a few examples of things that are based on my paper. So we can just focus on the first line here. So what is shown here is a fit to this coefficient C9 BSEE. So it means this is now a 4-fermion contact interaction which contains a p quark, a strange quark, and 2 electrons. And C9 says it's a vector current for the electrons. And then you switch on that Wilson coefficient and you ask what is the best fit value for this Wilson coefficient and how much better does this best fit point do compared to the standard model. And and this depends to some extent which data you are including. Here we are including the lepton flavor universality ratios, so Rk and Rkstar, and also p sub s3 plus v minus, which arguably are the cleanest, the theoretically cleanest observables. And here in this column, we also include all the other information, p sub s to phi mu, p to k star mu, p to k mu branching ratios, p5 prime, and all those angular observables. And well, in the case of the electrons, the two columns are actually almost identical because all these other information, this dirty information, the information about observables which are subject to large Adronic uncertainties, they are related to measurements with muons. So if you switch on new physics and electrons, that actually has no impact. The only impact is really these lepton flavor universality ratios, Rk and Rkstar, and those measurements prefer the coefficient C9 for electrons of around 0.7, and it's a sort of a 4 sigma improvement over the standard model. And this 4 sigma just corresponds to adding up these various 2, 2.5, and 3 sigmas in these lepton flavor universality ratios. If instead we do the same thing now with new physics and muons, one does see a difference between this column and this column, because if we now again we focus on the first line here, C9 BS mu, so now we have a 4-fermion contact interaction involving a p quark, a strange quark, and 2 muons. So now if we switch on this coefficient, again we can explain the lepton flavor universality ratios and p sub s3 plus v minus, and if we do that, we find again a best fit value of around 0.7 with the same pull with respect to the standard model. So now instead of enhancing the rate into electrons to get Rk and Rkstar, we're now reducing the rate into muons, but we can get sort of the same quality of the fit. But once we include all the other information of absolute branching ratios and angular observables as well, we find that the best fit point is still more or less the same, but now the pull increases above 5 sigma. But that has to be taken with a grain of salt, because now that includes all those observables which are theoretically maybe not under very good control.
So sorry, I have a question.
Yeah.
So when you do this, you fix the other, for example, the electron or the other Wilson coefficient. So you have to turn it on one by one.
This is one by one. So you only switch on one coefficient at a time and set all the others to 0.
Okay. Okay. Thank you.
And yeah, so just this comment of caution here, though. Overall, of course, one has this very high preference for new physics in some of these Wilson coefficients, particular C9, also C10, or combination of C9 and C10, and one has to be careful and wants to interpret that as a global significance. So what we're doing here is we're looking at pull values, which are differences in chi-squareds between the standard model point and the best fit point of these new physics scenarios. But because there are, of course, many different new physics scenarios that one can look at, so in some sense, it's more likely that one finds some new physics scenarios that does work, because there are many new physics scenarios that one can check. So there's, in some sense, a look elsewhere effect, and people try to estimate what that effect is, and actually there have been papers written by experimentalists of the LHCb calibration, which try to really quantify that, and they come to the conclusion that there's a global significance of all these discrepancies if you take into account the looks elsewhere effect, is around 3.9 sigma. So the fact
how do you define look elsewhere effect in the theory space? That's
I don't know exactly. So I don't claim that I understand this paper, but they claim that they know what to do and that they can quantify that.
Okay. That's that, you know, in the when the experimental says the looks also effect, they basically, you know, they do the scan over the masses, right? So we know what they are doing, but this is the looks elsewhere effect in the theory space, right? Not in the
yes.
I see. Okay.
In any case, so that there is high preference for the new physics, and it's hard to. I have trouble quantifying precisely how big the significance of that thing is, but it is certainly at the level which is interesting and which I think which justifies that there is quite a bit of effort going into these types of studies.
Wolfgang, sorry, the last line is very interesting. When you have C9 and equals to minus C10, you increase the pool. But if you have them equal, you reduce the pool. How do you interpret that result?
Yes, very good. So if you have the opposite sign, if you go back to this slide here, if you have C9 equals minus C10, that means you have a relative sign between a vector current and the axial vector current. So that's a V minus A current, so a left-handed current for the muons. So if left-handed muons are involved, then the fit is very good. Instead, if you have a plus sign in between, that corresponds to a right-handed current. For right-handed muons, the fit doesn't work very well. So you want left-handed muons to be involved, and then the fit works very well.
Okay, so that is suggestion for the model builder to construct the model.
Yes, exactly.
Okay, thanks.
From a model building point of view, you want either left-handed muons or things that couple vectorially to muons. Those two options gives the best fits.
So that difference comes from the P5 prime or the differential distributions, or
a couple of things. So P5 prime is one observable, I believe, which does play a role here, but it's also the branching ratios themselves. If we have right-handed currents for the muons, then there's an anti-correlation between the B2K and the B2K star decays. So whenever you try to increase, or let's say you want to decrease the B2K decays, then you increase the B2K star decays and the other way around.
Do you know why is that?
That comes from the fact that B2K is a pseudoscalar to pseudoscalar transition, while B2K star is a pseudoscalar to vector transition. So they depend differently on the chirality of the particles that are involved. And for right-handed muons, you get this anti-correlation, and for left-handed muons, you get a correlation between those.
Oh, okay, get it. Thank you.
And actually, one can see that, and I mean, I have here a plot of C9 versus C10. So a two-dimensional plane where we now switch on those two Wilson coefficients at a time, those two simultaneously by setting everything else to 0. And this first plot only shows the lepton flavor universality ratios. So RK and RK star, and they prefer this blue band here. So that's a broad range of C9 and C10 values that work, and there's sort of a large degeneracy along that diagonal line here. And if one switches on all the other constraints as well, B sub S to mu plus C minus branching ratio, that prefers the yellow region here, and the various other B2S mu observables, P5 prime and the individual branching ratios, they prefer this orange region. And then if you combine everything, you get the red region as the global fit of everything. And it's sort of it's non-trivial that there is actually overlap between those various regions, so that is indication that all those various discrepancies that they line up consistently and that they can be explained by consistently explained by new physics that shows up in C9 and C10. And so there's this diagonal line here, this gray diagonal line that corresponds to the line where C9 equals minus C10. So the best fit point is sort of between that line where C9 equals minus C10 and only C9. So there seems to be certainly preference for non-zero C9, and if you if you go to C9 equals minus C10, it works even slightly better. But the best thing you can do is to sit here in this point here, where you have a C9 and a bit of C10 as well. And the best fit points are shown here. Based on those fits, one can make predictions for other lepton flavor universality ratios. So that is shown in this plot here. There's the RK, the current measurement of RK in the Q square bin from 1 to 6, compared to the standard model prediction. And then the blue would be just the output of the fit. So if you fit all the data and then ask the fit what is the prediction for RK, that is the blue band, and of course it agrees very well with the measurement, because the measurement is sort of what fixes the new physics region in the first place. But then you can predict all the other things as well. You can predict RK star in various different Q square bins, R phi also in different Q square bins, and the prediction roughly is that all those R ratios should be around 0.8. And so of course it would be interesting then to see when more and more experimental results become available, if they really will line up at this 0.8 value, or RK star. At the moment, the measurements that exist are quite a bit low. So the prediction would be, if it's a new physics effect, all these things should move up to around 0.8, and that's where the new physics prediction would be. For this RK star in this very low Q square bin, there the standard model prediction is lower and the new physics prediction is a bit higher. So that is a special case, because there RK star is dominated by a photon contribution, P2K star photon, so actually an on-shell photon, which then goes into E plus E minus or mu plus E minus. And there the situation is different. So there the new physics effect is sort of diluted, while the standard model prediction is reduced, because you go to this very low Q square ranges where the different phase space for electrons and muons starts to play a role. But for all the other things, it's this prediction of around 0.8, and yeah, hopefully future measurements of these ratios will be compatible with this prediction. Now coming back to the new physics scale, that was something that I mentioned at the very beginning. So if one has now these anomalies, one can extract a possible scale for new physics, and that scale will depend on what one assumes for the new physics coupling. So what one actually gets information on is always the ratio of coupling divided by the scale squared. So if you say the coupling should be as big as 4 pi, you get a scale of which is actually very large, around 120 TeV. If you say that the new physics coupling is 1, so some very generic tree-level new physics contribution, then the scale is around 35 TeV. If it's a CKM suppressed, or if it's loop suppressed, or if it's CKM and loop suppressed, then you get scales which can be also much lower, 7 TeV, 3 TeV, 0.6 TeV. So there's a broad range of possible new physics scales that could be behind these anomalies, but there's an upper bound, so it can't be, so whatever new physics it is, it can't be heavier than around 100 TeV. Otherwise, it wouldn't be able to produce these effects that we're observing in rare B decays.
So that's the motivation for 100 TeV collider.
Yes. So if those rare B decay anomalies turn out to be actual signs in the physics, then there's a very good motivation to build a 100 TeV collider.
That 100 TeV, it's like what we expect from general B decay, right? You have new physics in B decay, and the scale is about 100 TeV. Yes.
So that lines up with these generic expectations that one can have for rare B decays. So that's exactly right. In terms of a simplified model, so many years ago, we looked at a C prime model that can explain those anomalies. It's a C prime gauge boson that is based on gauging the difference of muon number and tau number. So in the standard model, the difference of muon number and tau number is anomaly free. So you can gauge that symmetry. And you get a C prime gauge boson which couples vectorially to muons. So you get contributions to C9 in that way, if you couple the C prime also in a flavor violating way to B quarks and strange quarks. And the way you can do it, one way of doing it is to introduce heavy vector-like quarks which couple to the C prime and then mix with the standard model B quark and the standard model strange quark. So you need these heavy vector-like fermions, masses typically in the few to several, maybe 10 TeV range, and you also need a scalar that breaks muon number minus tau number. On the one hand, the scalar will give mass to the C prime, and it also will facilitate this mixing between the vector-like fermions and the standard model fermions.
So if you want to modify instead the electron channel, you can modify this by ELE minus EL tau, something like that.
Yes, you can do that. You can do that. If you couple the Z prime to electrons, however, then there are stronger constraints. Actually, there are constraints then from lab that you need to take into account, and those you automatically avoid from when you couple it to muons and taus only. But yes, certainly, if you do LE minus L tau or even LE minus L mu, these are also models that you can look at, and I believe also those models are able to explain these p-physics anomalies.
So can you specify which constant from lab?
That would be just E plus E minus going to E plus E minus, just and then they actually have searches for these types of contact interactions. So the C prime could be much heavier than the center of mass energy of lab. You still would see its effect indirectly in the I guess it would be in the just in the cross section of E plus E minus going to E plus E minus. So they do have searches for contact interactions for 4 electron contact interactions. Yes, and one thing that I should always mention in this context, when we first wrote this paper, the anomaly that we tried to explain was the P5 prime anomaly, which was out already at that time. But the first RK and Rtstar measurements actually came slightly after that. So we actually have a prediction that lepton flavor universality should be violated in this paper, and that's actually what then they since then they're seeing in the Arcane Rtstar measurements. If you look at the parameter space of that Z prime model, there's actually a vast range of Z prime masses which are possible. So as long as the Z prime is above the B meson mass, let's say, or significantly above, so let's say around 10 GeV or so, it can explain the B anomalies in this white region here. So the gray regions are all excluded by existing measurements. Important constraints come from B sub S mixing, also direct searches from at the LHC. There are neutrino scattering experiments which are relevant. There are lab constraints, but these are now different constraints. These are now loop level induced corrections to Z couplings, where the Z prime could play a role. At very, very low masses, you would have problems with Big Bang nucleosynthesis, direct searches as Babar, but these are things that are relevant at low masses. And this high mass regime, it's mainly B sub S mixing and direct LHC searches, which sort of constrain the available parameter space. But as long as you tune the gauge coupling of that Z prime accordingly, there's a broad range of Z prime masses which are compatible with explaining the anomalies. Interestingly, the C prime could also explain the G-2 anomaly, But this only works for very, very low masses. So only if the C prime is around 100 MeV or so. One could explain the G-2 of the muon with that C prime. So it's not compatible with the B anomalies. So you can either explain G-2 or you can explain the B anomalies, but you can't do both things at the same time in the context of this model. There are few interesting things about this model. So this the model is based on gauging muon number and tau number, and you gauge the difference. That means the coupling to muon and the coupling to taus is the same but has the opposite sign. That means there will be opposite effects, opposite Nifisik effects in the mu plus E minus channel and the tau plus tau minus channel, and there will be no effect in the E plus E minus channel. So what this model predicts is that all decays with electrons in the final state should be standard model-like, and then whenever you see an effect in the mu plus E minus final state, you would expect the opposite effect in tau plus tau minus. So, for example, if you look at all the muonic branching ratios, and if they are suppressed by 15% or 20%, you would expect that the branching ratios with taus in the final state, that they are enhanced by 15% or 20%. And for example, this P5 prime observable, if that is above the standard model prediction for the muons, it should be below the standard model predictions for the taus, etc.
But which one is easier to see, the discrepancy in the tau final state or in the E plus E minus final state?
Very good. Taus are extremely complicated. So electrons are already somewhat complicated, but taus are even much, much more complicated. So we don't even have any observation of those decays with taus in the final state. The existing sensitivities are orders of magnitude worse than the sensitivities you would need to actually measure those things. So at the LHC and also at Bell 2, for example, it won't be possible to actually see that effects in taus. There are prospects at future E plus E minus colliders. So people are talking about these Terra Z factories, FCCEE or CEPC in China. And there one actually might be able to measure the decays with taus. So if such a machine ever gets built, then one could have hopes in order to detect the effects in the tau final states.
So just because you cannot reconstruct the tau at all, right?
Exactly. At the LHC and also at Bell 2, it's very, very difficult to reconstruct the taus. You always have at least, well, if you have two taus, you have at least two neutrinos in the final state. So at the LHC, that's basically hopeless. At Bell 2, I think you have better chances, but it's still very, very difficult, and they don't have enough statistics there to make reasonable measurements.
I see. So you just have to wait for this thing to be.
Yes, yes. So if it is a C prime model, then the confirmation has to wait until a CEPC or FCCEE is built in, I don't know, 20 or 30 years or whenever that thing will get built.
When we almost retired or maybe retired.
Here's actually a list of other predictions that this model is making. The first thing is that there should be no lepton flavor violation. There's lepton flavor universality violation, but there's no lepton flavor violation. So that means that there shouldn't be any decays like B sub S to tau mu or B to K star tau mu or something like that. It's always the diagonal thing that exists, but it's not, the off-diagonal couplings don't exist in that model. And that's different to many other models that have been proposed to explain the anomalies. So many other models predict large rates for these lepton flavor violating decay modes. But this model predicts that those rates should be negligible. The other thing is,
models like quarks, right?
Say it again?
Other models is like leptoquarks model or.
Yes, exactly. Mainly leptoquark models are being considered. Yeah.
Yeah. Okay. So they predict B sub S to tau mu and these lepton flavor violation decays. I see.
Yes.
Okay.
The other thing that this model predicts is that B sub S to B plus B minus should be standard model-like. And that has to do with the fact that the coupling to muons in this model are vector-like. and I think we had discussed it very briefly at some point in this table here. So we have a C9, which leads to 0 effects in B sub S2 plus or minus. So B sub S2 plus or minus is predicted to be standard model like in this minus tau model. And again, that's in contrast to many other models that have been written down to explain the anomalies. And this would be a very important test or offset model if with future data this small 2 sigma discrepancy in B sub S2 plus or minus persists, or if it goes away. If it persists, then this model could be ruled out in that way. Another thing that this model predicts is that the neutrino decays should be standard model like. So B2K nu nu and B2K star nu nu. And it's a funny reason because it does predict effects in the individual neutrino flavors. So B2K muon neutrino is suppressed, but B2K tau neutrino is enhanced. But in the experiment, you can't measure the individual neutrino flavor, so you just take a sum of all of that, and then the effect cancels out, it gets washed out. So effectively, this B2K nu nu decay is standard model like in this model. Well, again, it's in many other models that's not the case. So it would be another thing, another way of distinguishing this model from these lepton quark models that many people are looking at. We looked at extended versions of this model. So one can, instead of gauging muon number minus tau number, one can try to gauge another linear combination of anomaly-free symmetries of the standard model. And there's sort of a 4-parameter family of possible gauge symmetries that one can look at. It's a combination of hypercharge and then a baryon number and the 3 individual lepton numbers. And one can play around with those models. I mean, they are much more complicated now because one has much more free parameters. It depends which linear combination of those symmetries one is gauging. Interesting thing that comes out here is that the axial vector currents are necessarily lepton flavor universal in these models. That's one thing that one can look at. And one also has mixing of C bosons with the C prime bosons. So these models tend to be much stronger constraint than the nu minus tau, which doesn't necessarily have to mix with the standard model Z. So this just as a side comment. So before coming to the end, here's just a plot which shows future prospects for the measurements of Rk and Rtstar. This plot is a bit outdated. It's a few years old. So with the pandemic, everything sort of shifted by probably a couple of years at least to the right in that plot, and probably there would have been anyway other delays. So 2 to 3 years switching that thing or moving that thing to the right is probably the good thing to do. But overall, the prospects are pretty good. So these are the projected uncertainties of Rk and Rtstar as a function of time. And over time, LHCb and also BEL2, they should reach the few percent level precision in various decay modes. And for Rk and Rtstar, LHCb should eventually even reach the sort of the sub-percent precision at the end of the high luminosity run of the LHC. Maybe also Atlas and DMS might be able to say something. Less clear exactly what their prospects are, but they should also be able to do some measurements at least. And another thing that I mentioned, I think earlier, one can also try to do lepton flavor entirety tests with angular distributions, even though the theory interpretation is a bit more complicated. But overall, there are good prospects to sort of get to the few percent level precision in many of these lepton flavor universality ratios in let's say the next 5 to 10 years or so. And that's a summary. So I showed that there are various results in rare B decays over the last several years, which show these discrepancies with standard model predictions. Of particular interest are these lepton flavor universality ratios, Rk and Rtstar, because they are theoretically very clean. And if the significance of those discrepancies continues to grow with more statistics, then those would be a very clear indication of early physics effects. And the recent updates that we've seen from LHCb earlier this year and then very recently, a couple of weeks ago, are very reassuring in this context. One can speculate what type of new physics it could be. So my model would be this numerous tau model, and of course, it'd be very interesting to see what comes out from the next round of the experimental updates. Okay, so that's it. Thanks a lot.
Thank you.
Thanks.
Yeah, thank you.
Any questions? Thank you, Wolfgang.
So do you have new fit for C9 and C10 with the newest result of LHCb?
We haven't done that yet. I don't expect it to be to have a big impact. If you look at because the uncertainties are so large compared to Arcane, which has sort of a 4% uncertainty. These are 15 to 20% uncertainty. So it probably will not have any visible impact on the plots or the numbers that we're showing, or maybe a tiny impact, but nothing really significant.
Okay, so we can still use the number in the table that you saw.
Yes.
Before.
Yes.
Okay, thank you.
The central values are kind of the same with others, right?
Yes. Yes. So the central values are
0.6,
very similar
yeah.
to Rtstar here.
Yeah. Yeah. So really, even the central value wouldn't shift by that much.
Yeah.
So for RK, LHCb has analyzed all their data already, right?
Not yet. So,
okay.
So these Rtstar measurements, for example, they are done with run 1 data.
Okay.
So we don't have a run 2 update of those results yet. So that is something that is supposed to come at some point. I don't know when. They should have shown that already years ago, but they are taking the time though.
But for RK, just RK, not Rtstar.
RK is the yes, RK is the full data set that they have.
So now we have to wait for other experiment to either verify or confirm this now, right?
Yes, I mean LHCb will continue data taking then in run 3, and they will probably again probably not like double the statistics or so in run 3 or even more, and you can get more data. Those uncertainties from LHCb will get reduced, and then Bell 2 will enter the game now in a few years from now. So Bell 2 is already data taking, and they're slowly ramping up their luminosity. So in a few years time scale, they should be able to have uncertainties that are probably not yet as good as the one from LHCb, but still interesting in order to confirm or reject those numbers from LHCb.
I see.
Other questions? Really, you can ask any questions. Well, even the easier one. Kiri, you want to ask questions?
I would like to ask why the discrepancy in the Rtstar is a little bit larger than Rk.
Well, that's what the experimental analysis says of their data so far, though it's not what you would expect from new physics. So from a new physics point of view, you would probably expect that both of them are comparable. So the central values are expected to be similar. So if it is really a new physics effect, you would expect those numbers to sort of stabilize and become more similar with more data. I mean, but given the current uncertainties, they're not perfectly in agreement, but they're reasonably in agreement that this is sort of the new physics interpretation that both of those values should converge to a common value in the future.
So if the central value stays the same, like you would guess like after IC run 3, then it will get settled, right? Like we have 5 sigma or something like that.
Yes.
By the time.
Yes. It would be puzzling though if RK star stays so low. So if RK star stays at this 0.66, let's say, and the uncertainty gets smaller and smaller, and RK stays as high as 0.85, then this is hard to explain what's going on. Then I don't know exactly what the conclusion would be.
Yeah, because it's not in the lepton sector anymore. It's in hadronic sector, but like how strange it will be, like.
Yes.
Because it's basically the same, right?
At the quark level, it's the same transition. It's always a B quark going to a strange quark. It's only the sort of the spectator quark which is changing, and it's very hard to. Well, I think one could come up with new physics models that do that, but it wouldn't be anymore the sort of the simple four-fermi contact interaction, and that's it. So you would need much more sophisticated models to do something like that. And then I guess it would become less convincing that it is actually a near physics effect if you have to create all kinds of complicated models to do that.
Yeah, could it come from the well, but it's RK, right? There is not so much hadronic QCD effects on there. It wouldn't come from so if the difference turns out to be true, then at least experimentally, like there is no QCD plays around that.
Yes. Then one would need to argue that something is wrong in their detector. I don't know. Maybe they don't understand how to reconstruct electrons, or I don't know, something like that.
Any other questions?
Yeah, just wonder what is the current status of the FCCEE? Because in Europe, is it approved or?
I don't think it's approved. So there was this European strategy update, was it a year ago or so, or a bit more than a year ago, and there I think it's mentioned as a part of a high priority program to go to a 100 TeV glider eventually. But I think it's formulated sufficiently vaguely that nobody really knows what will be happening. But it's a possible future for CERN, but it's very far from being decided what exactly will happen.
So the status is not determined yet. Is still under being review, or?
I think so. Yeah. I mean, there have been various conceptual papers laying out the physics program of such a machine, but I think the main problem is simply that it's very, very expensive to build and to run, and it's that will be the main question. If CERN can secure all the funding that they would need to build something like that, I think there's certainly from the side of CERN, I think there's certainly the will to do something like that, and there's motivation to do something like that. But it's mainly a question about the funding.
I see. How about the CEPC?
There I don't know exactly. Also, there the situation is not clear as far as I know. So the funding situation. I mean, I think there was. I mean, this is what I heard. I think a couple of years ago that they have these nationwide projects, where many different large-scale projects are competing for funding, so large-scale science projects, and I think they are still in that competition, but it's not clear if they actually will get funding and if they actually can go ahead and build that thing. So at the moment, they're in the sort of design phase of that machine, and they have some funding to do these design studies, but it's unclear if they actually will be able to build it or not.
From B-physics or flavor physics future, is there any SYCB, which is with the ASEAN Ballet 2, is there any future colliders for that subject? The flavors.
So quite a bit of background noise now, but I think your question is what are the new B-physics experiments in the future? Yes.
Exactly.
So FCCEE or CEPC, they would be very interesting in the context of flavor physics, because there the plan is to run at least some time on the Z pole. So basically repeat the lab program of precision Z physics. And if you produce, let's say, a 10 to the 12 Z bosons, they have a large branching fraction into BB bar. So Z boson going into BB bar, so you're just producing lots and lots of B hadrons at such a machine. And you can do a very nice B physics program in that context.
But so there is no special built machine like Bell or
No.
There is no.
So,
nothing. So
I mean, Bell 2 is running now and probably will run for another decade or so until they reach their design goals.
Yeah.
And after that, there is no dedicated B physics experiment planned, at least not that I know of.
So I see. So the future really depends on this FCC for everybody.
Yeah.
I see.
Actually, here from the talk, it seems that the new physics coming from the muon sector. So I heard someone there proposed the muon collider. Maybe it can also resolve this kind of thing.
Yes. If a muon collider ever gets built, that would be also very interesting in this context. So there you're almost guaranteed to see something. If something couples to muons to explain the anomalies, then at the muon collider it's very hard to miss that new physics. But I think muon colliders are even further away from this E plus E minus collider. So that's very, very unclear to me if a muon collider could ever be built. I think there are many technological challenges to do something like that. So I wouldn't hold my breath for a muon collider.
I guess it will happen not after we retire, but after we pass away or something.
Yes.
That's even. That's very far in the future.
So Wolfgang, can I ask some silly question now?
Sure.
So I don't know if the message that I'm getting from your talk is correct or not, but it seems like if we were to take all these B anomalies seriously, right? Leptoquark should be out now, right? I mean, it cannot accommodate all these anomalies.
Leptoquark also works. I mean, the thing is that I only showed the C prime model, but there are leptoquark models that work. The only thing is that leptoquarks make different predictions for other decay modes, which have not been well tested so far.
Oh, so you can have the scalar that can accommodate all these. Okay.
Yes, you can have a leptoquark model, and it explains the anomalies perfectly, and it makes predictions for various other things. It's just that these other things, so the predictions of the Z prime model and the prediction of the leptoquark models are different for these other observers. But leptoquark models are perfectly fine to explain the anomalies.
Oh, okay. Thanks.
So B sub S tau mu is going to be measured at the LICB, right? It's not that hard, is it? It's hard, but
it is somewhat hard. I mean, they will try to search for it. I mean, the standard model prediction is basically 0, so you will never see these decays if it's only the standard model. And then for new physics predictions, then the question is which model it is. If there is some leptoquark model which explains the anomalies, some of these leptoquark models predict that the rate should be as high that they actually should be able to see it. But other models predict that the rate should be sort of smallish, and then they wouldn't be able to see it. So some models can be tested by LHCb in this decay mode.
I see. So their LICB is trying or will try to measure this channel, right?
Yeah.
Because it's not that crazy.
Yeah.
You only miss one thing, the 1 2 3 nodes.
Right.
We still have muon to live. So
yes.
I see. That's quite interesting. Other questions? Kidir or Apriyadi, you can ask silly questions as well, as silly as you want.
No, not yet. Maybe Apriyadi.
No. Okay. Well, then if there is no more questions, I think we can send Wolfgang home.
No. Maybe
What is
yeah.
it?
Please come to Indonesia if you have time in the future.
Yes, come to Indonesia. That's the
Have you
message.
visited Indonesia before?
Sure.
In Taiwan.
It's well, yeah, we Patipan might say come to Thailand as well, but I'll say to Patipan, come to Indonesia.
Yeah, Wolfgang, you and Stefania should come visit either
Yes,
Thailand
yes.
or Indonesia. Yeah.
Yes, we'll be happy to do
Thailand
that.
or Indonesia. I don't know which part of California you live. Like, is it cold or warm? I have no idea.
It's
it,
northern part of California, so it's not extremely warm, but it's also not cold. So it's close to San Francisco where we are.
Oh, it's close to San. Okay. So it's you have some microclimates there, which is colder than usual. I see. It's like.
Yes, I mean in the evenings it gets pretty cold, but usually during the day it's typically 20 degrees Celsius.
Oh, 20. Well, 20 is what we have in the morning.
But you've been in Canada, right? So this is tropic for you.
Exactly.
I don't know. Stefania is from Italy, so she might complain about Canada even. And then
yeah, I mean, in terms of weather, she likes it here. So
maybe she'll like it even more down. If you go to Thailand and Patipan will take you to Pattaya, we might choose one of those. So come to any of this country and we'll treat you.
Sounds good.
At some point, yeah. Well,
Yeah,
probably is like.
Yeah, we are trying to promote the Indonesian standard model scientists here. So
Sure.
we hope the group is getting bigger, so we can have some conference in Bali. Maybe it would be fun. But it's still in the far future. We just introduced you the very small community that we have right now.
Yeah. So this is what as I told you last time, right? This is all we have in Indonesia now, or maybe plus one or two people. So we are still building. But I think Thailand has slightly bigger, or at least they have CMS there, CMS people there. We don't have any CMS.
We have experimenters here.
Yeah, we don't have any. We have Alice people, right? That's it. Not even LCB. If we had the LCB, then it's more fun. But we have Alice. We don't know how to talk with them.
But he'll go to management.
Yeah. So yeah. Thank you very much for
Thank you.
your night to talk with us.
There's again some background noise. I couldn't.
Yeah, you have so much noise, Julio. But yeah, thank you for spending your night giving us.
Sure. Thanks for the invitation. It was a pleasure to do that.
Again, maybe at some point if there is new LSCB results that we are interested in, we'll get right again. But yeah, thanks a lot. Thanks a lot for giving us this great review. So if there is no more questions, I think we can send Wolfgang home. And
all right, it was good seeing you, and take care and see you another time then.
Take care. Say hi to
Okay, have a good night, Wolfgang.
Bye bye.
Thank you. Bye bye.
Thank you very much.
See ya.
Bye bye.
So yeah, next week, minggu depan saya ngomong
Lecture-nya
berdasarkan
si
permintaan.
Rohini ya.